Good evening, everyone. My name is Harini. I'm a PhD student in Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So currently, I'm doing NPTEL TA-ship for the course Watershed Hydrology offered by Professor Rajendra Prasad sir from IIT Kharagpur. And in today's lecture, we will be talking about a flood routing, and there are different methods how we will do flood routing, like based on whether we are applying in reservoirs or on channels. There are two types, reservoir and channel routing. And if we are like considering which kind of routing we are applying, whether we are considering only continuity equation or we are considering momentum equation as well, then we have two types of routing, hydrological and hydraulic routing. So we will be discussing about these methods, and also we will solve few problems related to it and also look into some theory questions related to this topic. So now let's start with what is exactly flood routing. So flood routing is a method of determining the time and magnitude of a flood wave at a section of a river by utilizing the data at the upstream of the river. Okay, so flood routing. It is a technique of determining the time and magnitude of a flood wave at a section of a river by utilizing the data of flow at one or more upstream sections. Okay, so if you remember, if we have a watershed like this is our stream network, and we need to find the flood hydrograph at this point, then what we will do is we use the data and the upstream parts of the catchment. Suppose if we have data at multiple location, or if we have data at a single location in the upstream, so we know the flood hydrograph at that point, and using technique called flood routing, if we know this hydrograph, then we can route it and find the flood hydrograph at the downstream section. So we need the data at the upstream of the catchment to get the data or the unknown data at the downstream of the catchment. Okay. Suppose if we have multiple locations, we have the flow data, then using these multiple locations we can understand the flood hydrograph at the downstream location using flood routing method. Okay, so why are we doing this? We are doing this because it helps us in understanding the dynamics of the water movement and its impact on the infrastructure. Suppose if there is any flood that's going to happen, and we have the data that here there is a maximum water level that is recorded, so we can route it and we can estimate the flood level at this point also. So using that, we know whether there needs to be an evacuation that has to be done, or there will be any damage, like whether the water that is coming downstream will inundate the areas around it, like agricultural land or any buildings that are there, or any other infrastructures like industries or anything, whether they are going to be flooded. All this idea we will have, and then if we have that idea, then we can effectively manage it. Like suppose if we know that beforehand, we can ask the people to vacate it, or like we can divert the whatever flood water that is coming to the downstream, so that this part won't get affected that much. Okay, so flood routing helps in understanding the dynamics in water movement its impact on infrastructure, and how to effectively manage and mitigate flood risk. Okay, so these are the advantages of why we are trying to do flood routing. Okay, so the moment of flood wave along the channel, with time and space, we will get the idea of it. Okay, so then let's talk about what are the different methods that are involved in routing. So first method is reservoir routing. It involves the study of how flood wave propagates through a reservoir or a storage structure, such as dam. So here, in this case, what we will be mostly doing is like if we have dam or reservoir, like kind of storage structure, we know how much of water is coming into the storage structure. Inflow, we have a storage structure, and from that, based on the inflow or the capacity of the reservoir, we will discharge the water outside. So now that we know, we have an idea of what is the inflow into the reservoir. By using reservoir routing, we can get an idea of how the outflow hydrograph looks like from a reservoir. So basically in reservoirs, what we will do is that if a reservoir will have a fixed amount of capacity, right? So, and if we know the inflow already, and if we know the future info at time step t plus delta t, and we know that this inflow at t plus delta t is causing flood in this area, then we have to release the water because the reservoir cannot hold more than it. Okay, so based on the storage capacity of the reservoir and also the amount of inflow that is coming, the outflow of the reservoir will be dependent. So that's why like we are separately talking about reservoir routing, and in case of channel routing, we don't have these reservoir structures. So suppose in a channel, at the upstream part, we have the hydrograph or inflow data, and we need to calculate the flow at the downstream part. Then what will happen is there might be some intermediate losses like evaporation or some losses that are occurring due to infiltration, or there is a diversion of water. Okay, so based on that, the flood level at this downstream part will be mostly the flood level will be lower than compared to this upstream. So we need to separate kind of flood routing in case of channels, and in case of reservoirs, we do different types of routing because it involves a component called storage. Okay, so why are we doing this in reservoir? It will be useful in deciding the location and capacity of reservoirs to meet specific requirements. So using this, like we can identify which parts of the uh, channel or the basin requires the storage structures, so that the downstream part won't get flooded. So and based on that, we will know how much capacity of reservoir is also required. Right. So routing will be helpful in deciding the location and capacity of the reservoir to meet the specific requirements. Okay, let's look into what are the key components of the reservoir routing. The first one is, as I have told, it will be inflow and outflow analysis. So the inflow can be due to the direct precipitation that is occurring in the reservoir. Okay, so whatever the direct precipitation that is occurring, and also the runoff from the upstream. Inflow can be direct precipitation, the runoff from upstream, upstream of the watershed, and also there can be some contribution from the tributaries. If you have any doubts, you can ask me, or you can uh, message it in the chat box. So the outflow in case of reservoirs is mostly controlled by the gates or spillways or any other hydrological structures. Controlled by gates or spillways mostly. So the next key component is the storage discharge relationship. So this is very important in a reservoir because the reservoir can only hold a particular amount of capacity. If the water inflow is more than that, it cannot hold, and there is a and it can lead to breakage of the reservoir or the dam structure also. So it is very important to have a storage discharge relationship, because if we here what we will do, we will get an idea is that if the storage level in the reservoir is at a particular level, then it will tell us how much of discharge should be done from the reservoir. So so that the inflow from the next time period or the inflow that is going to come will not exceed the storage capacity of the reservoir. Okay, so this is very important in the reservoir cases, and it's very important also in crucial for predicting how changes in storage influences the discharge downstream. Downstream is written as D slash S. Okay. And the third important component is that the hydraulic characteristics. So the hydraulic characteristics will be like the capacity of the reservoir, the shape, and the presence of the controlling structures. Okay, so these are important in how quickly the reservoir can observe the incoming flow, and also how quickly it can release the water downstream. Okay, so characteristics like capacity, shape, and presence of controlled structures in the reservoir. Okay. So based on the type of the discharge outside, we have two different equations for the discharge. This is the peak discharge will be equal to C into L into HW whole power 1.5. This is L is the width of the weir and H is the height difference. Okay. And in case of the outlet is a pipe, then we have other formula 2GH whole power 1.5. The outlet is a pipe. Okay. Okay. And how the hydrograph of the inflow and the outflow looks like is, suppose we have a inflow hydrograph like this. Because of the storage structure, there will be decrease in the peak of the inflow hydrograph when it is getting discharged from the reservoir. And also it won't be released instantly, right? So it will take time for the discharge to come out of the reservoir. So also the time base of the reservoir is increasing. You can see time base is increasing, and also there is an attenuation in peak. And also you can notice there is a time lag. The peak in the inflow is occurring before than the peak on the outflow hydrograph. So this time difference is called as time lag. Okay. So this is time and discharge. Also, one more important thing that you have to notice, the area in between the rising limb of both inflow and outflow hydrograph will give us the storage in the reservoir, the amount of water that is stored in the reservoir, and the area between the uh, falling limbs of the inflow and outflow hydrograph will give us the discharge from the reservoir. So generally, both these areas should be equal, because whatever this amount that we are storing will be discharged in the later time. So mostly these areas should be equal. This is discharge from storage. Okay. And then, so we have talked about how the reservoirs are affecting the inflow and outflow hydrograph. The time base of the outflow hydrograph is increased when compared to inflow hydrograph. Also, you can see there is a attenuation peak in the outflow hydrograph because of the storage that is occurring. So these are all the results of effect of storage structure on the hydrograph. Okay. So, and also you can see that the time to peak is also occurring at a later time step, not at the, so here, suppose if it is occurring in T1 hours, here it is occurring in T2 hours, right? So there is a lag in the peak flow of the outflow hydrograph when compared to inflow hydrograph. Time lag in the outflow hydrograph when compared with inflow hydrograph. Okay, so so first we have talked about what is, if you see, first we have talked about what is flood routing. And in the routing methods, first we have discussed, I have given slight idea about how, or what is reservoir routing and what we are doing, and how the reservoir structure is affecting the inflow and outflow hydrograph. So now let's look into what is the second type of routing, that is channel routing. So the in the case of channels, that is the stream channel, okay, there can be a change in the shape of the hydrograph as it travels down the uh, channel. Because of the, as I've discussed, there can be losses due to infiltration or evaporation, or also there can be the change in the cross section of the channel also, which can lead to the change in the shape of the hydrograph. So that we are going to study in the channel routing. So in this, we will be studying about study of change in shape of hydrograph as it travels down a channel. Okay, so here as similar to reservoir routing, we'll get an idea of the flood peak in attenuation, and also the time at which this high flood peak can occur. Okay, obtain information on flood peak attenuation and so duration of high flood levels. At what time the flood is going to occur, and also for how long it's going to stay, and what is the amount of flood peak that is going to receive in the downstream part. All this information can be obtained once you do a channel routing. Okay, so also it can be helpful in flood forecasting operations and flood prediction works. So if we have the data in the upstream part of the channel, then we can, if we have forecasting data or any other data, like a real-time data in the upstream location also, the flood won't be reaching the downstream part immediately. It will take some duration, like maybe in hours, right? So using flood routing, we can know how much of flood that can reach downstream. And before it reaches, only we will get an idea of how much flood it is going to reach. So we can do flood prediction. And if you have forecasting data in the upstream part, we can route it and get the forecasting data at the downstream location also, so that we know whether any floods are going to uh, there is a possibility of any flood in the recent time step, so that we can take some mitigation efforts and manage the flood. Okay, so now let's talk about different routing methods. So first one is lumped or hydrologic routing. Okay, so in this, what we are going to do is we are assuming that flow is only a function of time at a location. Since it's lump, meaning we are not considering the flow is a function of space. Okay, so it is we are saying that here we are assuming that flow is only a function of time at any location, and we will be only using equation of continuity for solving the routing problem. And the next type of routing method is a distributed or hydraulic routing method. So distributed, as we have studied in previous class, that means we are in any catchment, we are considering multiple grid points or multiple locations. So that means we are not averaging over the space or anything. So we are considering flow as a function of both time and space. Okay. And in this case, we use both equation of continuity and equation of momentum which takes care of the unsteady nature of the flow. Okay. So generally the lambda or hydrologic routing methods are the very simple methods because we are making a lot of assumptions. It will be simple and computationally it will be very easier. In case of distributed or hydraulic model, we have to solve a very huge differential equations, which will take a lot of computational time and effort. Also, but it will give more accurate results compared to the our lambda or hydraulic models. So it depends on the user or the modeler of what type of model you have to choose for your particular case study. Whether you will go with the hydrologic model, where you need immediate results within short time because the computational effort is less, and but even though the accuracy is little bit less, and or if you need a very accurate results, so you have to go with hydraulic routing. So now let's discuss about the hydrologic routing. So here we use very simple mass balance equation. Simple mass balance equation. So that is, if there is any inflow minus outflow will be equal to change in storage. So this we can write as I is inflow, O is outflow, and change in storage we can write as ds by dt. We are considering change in storage with respect to only time. Okay, since in the routing, we are only considering the flow is function of time and not on space and all. So we are only considering with respect to time the equation. Okay, so if for any small time interval, the equation, any small time interval delta t, the equation will become I minus O equal to delta S by delta T. So if you can bring delta T to the left hand side, it will be I into delta T minus O into delta T equal to delta S. So here delta T is, suppose we are taking as the difference between two time step T2 minus T1, then we will have inflow at T1 time step and also inflow at T2 time step, right? So what to use at these points? So we have to use the inflow at time step T1 or T2 or outflow at T1 or T2. But here delta is nothing but, S2 minus S1 because it's a change in storage at time step T1 and T2, right? So what to use this? So here what we will do is we will average the inflows and outflow terms here to avoid that uncertainty. So here this is the average inflow in time delta t, and this is average outflow in time delta t, and delta S is a change in storage. So the equation can be written as I1 plus I2 by 2 into delta t minus O1 plus O2 by 2 into delta t equal to S2 minus S1. So 1 and 2 represents the beginning and the end of the time delta t. Suppose like here T1 is the beginning of the time step for delta t and T2 is the end of the time step of delta t. Okay. So this is the basic concept that is involved in hydrologic routing. And when we are coming to hydraulic routing, here we will give a basic formula without any lateral flow. So equation of continuity for unsteady flow with no lateral flows can be written as dO by dx plus T into dy by dt equal to 0. So O is the outflow of the section, and then x is the um, length, and t is the top width of the section, y is the depth of the flow, and t is the time. So similarly, we have for to account for the momentum, we have Sandvanen's equation, which is dy by dx plus v by g into dv by dx plus 1 by g into dv by dt equal to S naught minus SF. Here S naught is the bed slope, SF is the slope of the energy line, and dV by dt will account for the local acceleration if you remember, and this will account for the velocity of flow at a section, like at the cross section, how it is varying the flow, and dy by dx is the change in the water depth with respect to the length. Okay. So now we will be talking about the hydraulic reservoir routing. So for the now, as I have told, if you are applying for reservoir or channel, we have two type hydraulic, whether it will be reservoir routing or channel routing. And in that also we have subdivisions of hydrological and hydraulic routing. So here we will be first looking into hydrologic reservoir routing. So in this, mainly what data is we required is, as you can see here, we need a data of storage versus elevation curve of reservoir. So the data that is required is storage, elevation, curve of reservoir, or and also outflow, elevation, curve of outlet. Okay. So here, remember here we are talking about the storage and elevation curve of reservoir. How much of the storage that the reservoir can take, and based on that, the elevation in the reservoir, we need that relationship, or we need a outflow elevation curve of outlet. So outlet like spillways or any other structure, that hydraulic structure that we are having on a reservoir, how much of the discharge that the outlet is giving based on the elevation, right? So remember, these two are the different. This is the storage elevation curve of reservoir, and the second one is outflow elevation curve of the outlet. Okay, so based on this data, we will develop a storage versus outflow curve can be developed, because these are the characteristic curves of the reservoir. So we will get this data from CWC or any other source, and from that we will develop a storage versus outflow. So if we know like S1 amount of storage is in the reservoir, what can be the outflow from the reservoir? We can develop the curve, and then this data can be obtained from that curve. So if you see, and the equation that is involved, since I have talked, this is a hydrological routing, and if you remember, the equation that we have written is I1 plus I2 into delta T minus O1 plus O2 by 2 into delta T is equal to S2 minus S1 is the equation related to hydrological routing. So for this, we are mainly getting the data. Like first we need an inflow hydrograph, what is the inflow into the reservoir, and also we need the outflow versus elevation curve of the reservoir, and then we will develop, and we have, and also we need storage versus elevation curve of the reservoir. Here outflow versus elevation curve of the outlet, and storage versus elevation curve of the reservoir. These three data sets we need for the calculation. And here what we are doing is we are assuming that the pre-flood level, before this uh, inflow hydrograph has occurred, the water level in the reservoir is 131.2 meters, and also we are taking the time step delta t as 12 hours. So how we will do step by step in this case is, so we have inflow hydrographs. So at each time step, we know what is the inflow values. So if we have the time interval first is from 0, since we are considering 12 hour interval, 0 to 12, 12 to 24, like this we will divide the time step. And at each time step in from 0 to 12, we know what is the inflow. And 12 to 14, we know what is the inflow, right? So I2 will be, if t equal to 1 hour, t plus 1 equal to 2 hours. So generally this is t and this is t plus 1. We can write it like that also. So I2 will be the next, whatever is coming in the next step of I1 will be written here. Okay, like that we will get I2 values. So if here is B, then we are bringing it over here. So like this, we will have the inflows at t time step t and also at t plus 1. And using that, by averaging them and multiplying with delta t, we will have the values of I1 plus I2 by 2 into delta t. Okay. So delta T, remember, generally the inflow will be in meter cube per second and the delta T we will be assuming will be in hours. So both should be in either time step, both the time terms will should be in either seconds or in hours. So here, since we are considering 12 hours as a difference, we are delta T should be 12 into, to convert in 12 hours, to convert it into seconds, we are multiplying with 3600 seconds. Okay. So like this, you have to do the calculation for column 5. Then you will have this term I1 plus I2 by 2 into delta T value. And then suppose here we are saying the elevation, the pre-flood level of the spillway is 131.2 meters. So if you see from this, okay, from this curve, the elevation is 131.2. Suppose it will be here, almost closer to 131 meters. Then the corresponding the discharge will be almost equal to 0, right? So we are saying it's 0. And in next time step, like we are assuming that the reservoir level is little bit above than 131.2 meters. So we are saying it is 131.3 meters. And corresponding to the 131.3 meters, we can get the discharge term from this curve. Okay. So if it is here, we can get the discharge outflow value from this. So if you know O1 and O2, we can easily calculate the O1 plus O2 by 2 into delta T. Here also you have to remember delta T is in hours, but the units of outflow are in meter cube per second. So you have to convert the hours into seconds for calculation. Otherwise, you will get values, the values won't be correct. So then you have both these terms, I1 plus I2 by 2 into delta T, O1 plus O2 by 2 into delta T. So by subtracting those two, we will get the change in storage. So the change in storage within a time interval is obtained from by subtracting column 5 and column 9. Okay. So total to get total storage, what we have to do it, we have to accumulate the value. So here if you have storage as S1, here S2, at this time step S3. So accumulation means, if you remember, when we are calculating cumulative rainfall also from instantaneous rainfall, for second time step it will be S1 plus S2. And for that third time step it will be S1 plus S2 plus S3. So like this we will get the total storage value at each time step. And then once we have the storage values, we can, if the storage is like 25 meters, so sorry, million meter cube, then we can get the elevation value also corresponding from the figure C, right? So from that we will get the elevation value also, in this time step. So also you have to make sure that the elevation over here and here should be matching at each time step mostly. So this is how we have to do hydrological reservoir routing. And in this we have different methods like the Pearls or ISD method. So here, if you remember, we need to have a lot of data, like how what is the outflow elevation curve and storage elevation curve. So instead of that, we are trying to rearrange the data sets, rearrange the equation. Suppose here we have I1 plus I2 by 2 into delta T minus O1 plus O2 by 2 into delta T equal to S2 minus S1. By rearranging it, we will have the pulse or IST method. IST means inflow storage discharge method. So in this, how we are writing the equation is I1 plus I2 by 2 into delta T plus S1 minus O1 by 2 into delta T is equal to S2 plus O2 by 2 into delta T. So this is the equation that we will be using that we will be solving in this method, okay, to calculate the S2 and O2 values for the next time steps. So in this, if you remember, we know I1 plus, we can, if we have an inflow hydrograph, we can easily calculate I1 plus I2 by 2 easily. But we don't have an idea of how S1 or O1 can be evaluated. So these two terms are unknowns. So that's why, since we have the curves previously, which using that we solved the problem. So here also we need to develop curves like outflow versus S plus O by 2 into delta T. Also, we have to develop outflow versus S minus O by 2 into delta T and outflow versus storage. So these three curves are important. Like if you see here, we have outflow and also storage terms. Okay, storage S minus O delta T by 2, S plus O delta 2 by 2, all this we have. So how we will solve in this method is that, so we know inflow hydrograph is given. So we know at each time step what is the inflow value. So if we have 1 and 2 value, okay, so I1, I2, then for this time step, how we will calculate the I1 plus I2 by 2 into delta T. Okay, using these two values, we will calculate the average inflow and multiply with delta T. Remember, the delta T terms should be in seconds if the inflow is in meter cube per second. Okay, then if we have the outflow at time step O1, then if we have, suppose this is the O1 value, then what we can do is by drawing a line, we can get the value of S1 minus O1 into delta T by 2. This point. So this value will give us S1 minus O1 into delta T by 2. So this value we will keep it here. Okay. And correspondingly, so from this equation, we know now this term and this term. So if we add these two, we will know this term also. So by adding up column 3 and 5, we will get the term S plus O into delta T by 2. Okay. So once we know what is the, suppose that will be S2 plus O2 into delta T by 2 value. Okay. We know this. Then correspondingly, we can get the value of, from this graph, we can get the value of outflow at time step 2. So that we will keep it here, whatever the value. So like this, at each row, we will do the calculation. Is this clear, or if there are any doubts, you can ask me, or I can explain the doubts. So if there are no doubts, like I'll proceed further. So there are some assumptions related to this method, which we are considering that the reservoir water surface is horizontal, and the second one is outflow is a function of the storage volume, is a unique function of the storage volume only. And the third one is outflow rate varies linearly with time. Okay. So also because of this limitation, because of these assumptions, there are limitations in the in this method. It is like first we cannot apply for streams with sharper gradient, that is like approximately if it is greater than 0.57 meter per kilometer, then we cannot apply this method, and also it is not suitable for river or channel reaches. Because in case of rivers or channels, the boundary will change very rapidly. Also, the tides or rapidly raising hydrographs can occur. So I hope this is clear. So now let's look into this one more method called modified pearls or level pool method. This is almost similar to the previous method that we have talked about, but here we are trying to limit the number of curves that we are generating for the calculation purpose. Here we are only going to use outflow versus storage and also outflow versus S plus O into delta T by 2 curves. Okay, only these two curves we need to be generated, and the equation is modified as, let me write it here. So the equation is I1 plus I2 by 2 into delta T plus S1 minus O1 into delta T by 2 is equal to S2 plus O2 into delta T by 2. This is similar to whatever we used in the pulse method. Okay, so once we have inflow hydrograph, we know how to calculate I1 plus I2 by 2 into delta T. Remember that the delta T term should be in seconds. And so I hope it's clear how we will calculate I1 and I2. I1 is the flow at time step T, I2 is the flow at inflow at time step T plus 1. If we are doing for the time step. Okay. So basic inflow hydrograph is known. From that we can calculate I1 plus I2 by 2 into delta T. That's clear. Okay. First, initially they will give us the outflow value at time step at time 1. Okay. That is also known we are considering. So if we know this, if this is the O1 value, then corresponding, if from this curve we know what is the S1, the storage initially that is occurring. So using the O1 and S1, we can calculate S1 minus O1 into delta T by 2, right? So we know O1, and from this curve we know what is the S1. We just calculate S1 minus O1 into delta T by 2, and we'll fill it here. And then once we get these two, we know I1 plus I2 by 2 into delta T from the inflow hydrograph. This term also we have calculated. By adding these two, we will get this term, S2 plus O2 into delta T by 2. So once you have, suppose this is the S2 plus O2 into delta T by 2 value, correspondingly from this curve, we can get O2 value, right? So once you get O2 value, we will write it here. And then for the next time step, we'll do the same, follow the same steps. Okay, to calculate. Then again, using this O2, we will obtain the storage at S2, and then calculate S2 minus O2 into delta T by 2. And by adding the column 5 and 3, we will get S3 plus O3 into delta T by 2. And from this curve again, we can get what is the outflow at time step 4. Okay. I hope this is clear. If there are any questions related to hydrological routing, you can ask me, or we'll look into some form questions related to this. So if there are no questions, you can ask me whenever you have doubts. Not when I ask. Also, you can ask me other time also. Okay, so let's look into some questions related to this. So which of the following is closest in definition to the process of flood routing? Option A, determining flood hydrograph on upstream side with the use of upstream flow data. Option B is determining flood hydrograph on upstream side with the use of downstream flood data. Option C is determining flood hydrograph on downstream side with the use of upstream flood data. Option D is determining flood hydrograph on downstream side with the use of downstream flood data. So if you remember, in flood routing, once we have the data on the upstream, we are trying to evaluate we are trying to calculate the flood on the downstream part of the catchment using the upstream data. So the option is option C. So the next question is, how is flood routing categorized on the basis of its application? Option E, reservoir and channel routing. Option B, hydrologic and reservoir routing. Option C, channel and hydraulic routing. Option D, and hydrologic routing. So basic basis of application is where you are applying for reservoir or channel. So the category will be reservoir and channel routing. So the next question is, what are the key components of reservoir routing? Option A, an inflow and outflow analysis. Option B, storage discharge relationship. Option C, hydraulic characteristics. Option D is all of the above. So if you remember, in reservoir routing, inflow and outflow are very important. Also storage discharge relationship we need to know, and the hydraulic characteristics like the size, shape of the reservoir, everything we need to know. So the key components will be all of the above. So the next question is, what does the region between the falling limb of inflow and outflow hydrograph represent in hydrologic storage routing? That is option A, lost storage volume. Option B, accumulated storage volume. Option C, increased rate of storage decrease. Option D is a decreased rate of storage increase. So if you remember, we have drawn the inflow hydrograph and outflow hydrograph like this. So they're talking about falling limbs, the area between these are the falling limbs of the hydrograph. So this is the area that they are talking about. So if you remember, we have discussed that this is the discharge from the storage. This area corresponds to, and this is the storage that is occurring in the reservoir. So the option will be option A, lost storage volume. Okay. So the next question is, what happens when a flood wave passes through a reservoir? Option A, attenuated peak and shortened time base. Option B is attenuated peak and enlarged time base. Option C is amplified peak and shortened time base. Option D is amplified peak and enlarged time base. So, like I have drawn before, the inflow and outflow hydrograph from a reservoir will be like this. The time base is increasing for the outflow. So that means there is an enlarged time base, and also you can see the peak is attenuated. It's not amplified. Okay. So the answer is option B. The next question is, which of the following represents the basic continuity equation used in hydrologic routing? When I is the rate of inflow, Q is the rate of outflow, S is the storage, T is the time, and Y is the depth. So if you remember, the basic continuity equation we have written for the hydrologic routing is I minus Q equal to, Q is outflow, or Q I have written as O, outflow. Here we are saying Q is the outflow, is equal to ds by dt. So the the answer will be option B. Then the next question is, the Saint-Venant's continuity equation for unsteady flow in case of no lateral flow is given by which of the following? So Q is the outflow rate, T is the top width of the channel, and Y is the flow depth, X is the distance, and T is the time. So for that, what we have written is dq by dx plus T into dy by dt is equal to 0 is the continuity equation in case of hydraulic routing when in case of unsteady flow without any no lateral flow. Okay, so the answer will be option C. Then, which of the following relationship should be known to predict the reservoir elevation and outflow variation with time? Uh, Using reservoir routing. So, if you remember, we have talked about when we are doing reservoir routing, we need two type of data sets. First one is storage versus elevation of reservoir. Second one is elevation versus discharge or outflow of the outlet. Outlet can be any spillway or any hydraulic structure. So the answer will be outflow versus elevation relationship of a spillway, option C. The next question is, due to which of the following assumptions in hydrologic storage routing, it is also known as a level pool routing. So, if you remember, the assumptions are that the water level surface will be horizontal. Okay, and also outflow will be the function of only the unique function of storage volume, and outflow rate varies linearly with that time. So, for the level pool, that means we are saying the level, the horizontal water level, sorry, the reservoir water surface is horizontal, so the option is option D. Next question is, in hydrologic channel routing, storage is a function of which of the following? As I have told, it is a function of only outflow. So option B. In case of hydraulic routing, it's a function of both outflow and inflow. Okay, now let's look into how we will do hydraulic routing. So in case of reservoirs, we are only discussing about how we are doing hydrologic routing. But in case of channel, we will discussing about both hydrologic and hydraulic routing methods. So first it is hydrologic channel routing. This is used to model the movement of water through river channel or any convenience structure. So in this case, it is a unsteady and non-uniform flow in streams that we are addressing. The flood wave is an unsteady and non-uniform flow because of the channel characteristics and the variation of the inflow flood level. There we are observing an unsteady and non-uniform flow. Okay. So also here they are considering channel storage is a function of both inflow and outflow. Okay. If you remember, in reservoir routing, in hydrologic reservoir routing, we are considering storage as a outflow as function of reservoir storage only. But in case of hydrologic channel routing, channel storage is both function of inflow and outflow. We will be looking into how it is function of both inflow and outflow also. So here Lensley has showed that the channel storage can be sum of two types of storage, that is prism storage and wedge storage. So here if you see prism, to get the prism storage we draw a parallel line, uh, draw a line parallel to the bed. Okay, so at a fixed depth, we will draw the line, and the whatever volume that is falling within that will be the prism storage. So the prism storage will be fixed throughout because this will be the volume between these two lines which are parallel. Okay. And then we have a wet storage. This will be the uh, volume that is between the water surface. So this is the water surface, and also the this is the parallel line that we have drawn for prism, right? So there is no water in this. So wedge represents this volume. Okay. Here prism line is here, but water level line is here. So this is the volume or the storage that corresponds to the bed storage. So this will vary at each location. Okay. And it can be both positive or negative also, but prism storage is always positive. So in this, when there is no storage, there is a negative storage here for wedge case. And when there is huge storage than the prism storage, we have a positive wedge storage. Okay. I hope this part is clear. And here prism storage SP is a function of only outflow. But wedge storage SW is a function of inflow. Okay. So that's why we are saying the storage of the channel is function of both inflow and outflow. But individually, if you are seeing prism storage is a function of only outflow, and wedge storage is a function of only inflow. Okay. So the general expression for hydrologic channel routing is S equal to x into b into I by a whole power m by n plus 1 minus x into b into o by a whole power m by n. Here I is the inflow, o is the outflow, and x is the paying factor which accounts for relative effect of inflow and outflow on storage and other parameters. Sorry. And other parameters like a comma b comma m and n are just constants. Okay. So if the flow is uniform in prismatic channel, that is there is no wedge flow, wedge storage, then m will be equal to 1 and n is equal to 5 by 3. This implies m by n will be equal to 0.6. For natural channels, generally m by n value will be greater than 1. Okay. So also if storage is a function of only outflow, this will occur when only x is equal to 0. Suppose if we put x is equal to 0, this whole first term will be 0. So there the storage will be only function of outflow. Then it will become reservoir routing, hydrologic reservoir routing. But for natural channels, generally the x value generally the x value will vary between 0 to 0.4. Okay. So now let's look into the method, Muskingum method, which is most commonly used in channel routing. So it falls under the category of kinematic routing method. It is first developed by C.V. Theis and C.C. Hines in 1935 and applied for the first time in Muskingum River in Ohio. So that's why the name came Muskingum. And in this case, what they're doing is the flow in river channel is assumed as a function of channel storage, inflow hydrograph, and outflow hydrograph. Okay. Also the outflow at a particular reach is equal to weightage. Okay, weightage term W1 inflow at present time step plus W2 into outflow at a previous time step. In this method, we are assuming that m by n is equal to 1 and b by a is assumed as another constant k. Okay. So here the general expression will be by solving the previous equation that I have shown, as well the general equation will become as equal to k into x of I plus 1 minus x into O. Okay, here what are the x and k and x terms? X is the weightage factor and k is the storage time constant, which is approximately equal to time of travel of a flood wave through the channel breach. Okay, and the dimension will be in time. If in this case, if x is 0, and then what will happen? S equal to k into O. That means it's a linear storage or linear reservoir. As we have discussed previously in reservoir routing, the store outflow is function of storage only, right? So then this is also similar, it is similar, so that's why it can be termed as linear storage or linear reservoir. So here, if we have the data at two time step T1 and T1, T2, then how we will have the equation can be rewritten as S2 minus S1 equal to K into X of I2 minus I1 plus 1 minus X of O2 minus O1. And the continuity equation will be, as we have discussed previously, the continuity equation is I1 plus I2 by 2 into delta T minus O1 plus O2 by 2 into delta T is equal to S2 minus S1. So from these two equations, the final equation will be OT is equal to C0 into I2 plus C1 into I1 plus C2 into O1. So the outflow at time step T2 is equal to C0 into inflow at time step T2 plus C1 into inflow at time step T1 plus C2 into outflow at time step T1. Okay, here C0, C1, C2 are constants which are like functions of k and x. So C0 is equal to minus kx plus 0.5 times delta t by solving these two equations we'll get this kind of simplified equation, and we can get the values of 0, C0, C1, C2, and we are here writing what will be the C1, C2, C0, C1 and C2. Okay, plus 0.5 into delta t. Next, C1 is kx plus 0.5 delta t by k minus kx plus 0.5 delta t, and C2 is equal to k minus kx minus 0.5 delta t by k minus kx plus 0.5 delta t. Okay, here also there is one check that you have to do. Here, all the sum of all the constants C0, C1, C2 will be always equal to 1. Okay, and also here K and delta T are in both same units. It should be, if delta T is in hours, K also will be in hours. Delta T is in days, K also will be in days. Okay. So how we will solve the values of K and X? If we have the inflow data and all, then what we will do is first we will plot storage versus x into I plus 1 minus x into O curve. Okay. So here for different values of x, we will just plot the s versus this terms plot. So suppose if generally it will come in a loop. So if for x equal to 0.2, the xi plus 1 minus x into o versus s term is like this. And if for x equal to 3, 0.3, it is like this. But if for x equal to 0.1, it is like this. If whenever this generally as we have written, it is s equal to k into xi plus 1 minus x into o. So there should be only a linear relationship. That is, whenever you plot it also, there should be only a linear line. The plot should be a line. So here among the three terms, x equal to 0.1, x equal to 0.2, x equal to 0.3, x equal to 0.1 is closer to the linear line, right? There is no, like, it's the narrowest loop that can be formed. So then we will take that x equal to 0.1 is the best value. And then based on x equal to 0.1, we will find the values of x into I plus 1 minus x into O, and we'll plot s versus xi plus 1 minus x into O at x equal to 0.1. So if the lines xi plus 1 minus x into O and s, these points are like this, then we'll draw a best straight line, and the slope of this line will be k. Okay. So is this clear how we will calculate the x and k parameters of this Muskingum method? So if there are no doubts, we will look into how we will do hydraulic channel routing. So, it is mainly useful for flood events, for flood forecasting, floodplain management, and emergency response planning. And it is based on Saint Venant's equations of continuity and momentum. So the continuity equation will be dou q by dou x plus dou a by dou t is equal to 0. So remember, here we are talking about partial differentiations, not the total differentiations. Okay. And next, for momentum equation, it is 1 by a into dou q by dou t plus 1 by a into dou by dou x into q square by a plus g into dou y by dou x minus g into s naught minus sf is equal to 0. So here sf is the will account for the friction. So and s naught is the bed slope. This will be due to the flow is due to gravity, and this is the resistance that is offered by the friction, that is the roughness of the surface of the channel. Okay, and then here this term is the pressure term. Okay, pressure term, friction term, g into s naught is the gravity term, and this is local acceleration term. This is convective acceleration term. So, local acceleration will account for unsteady, and the convective acceleration will account for the non-uniform flow, which both are addressed in hydraulic routing methods. Okay, and here S naught is equal to minus dz by dx. Okay, so also here what we are trying to do is, in that very lengthy equation, when only if the friction terms are involved, then it is a kinematic wave with only friction terms. then the equation will become G into S naught minus SF is equal to 0. This is means S naught is equal to SF. This is the very simplest form of the distributed model. And the next is diffusive wave, which involves friction and pressure terms. That means G into dou y by dou x minus G into S naught minus SF is equal to 0. So from this it is dou y by dou x equal to S naught minus SF. This is the diffusive wave equation. And there is one more, dynamic wave, where all terms are included. Like we will include the local acceleration, convective acceleration, also pressure term, also the friction term. All these terms are included in the dynamic wave equation. It is a full hydrodynamic model. Okay, so as you go from top to down, the computational complexity will increase, effort will increase, and also the accuracy will increase. Okay, so based on the what type of model you require, like what type of method you need to know, like if you want more accurate results, then you should go for dynamic wave method. If you want a simplified, easy calculations with little less accuracy, you can go with the kinematic wave model. So here, there are like, as I have told about kinematic wave and dynamic waves, we will be discussing like how these two are differ. So if you see here, kinematic wave govern when inertial and pressure forces are dominated, are not important in the case of kinematic wave. We will be concentrating on the friction force and gravity, right? So it's a mostly unsteady and uniform flow, and it is mostly used for short duration flood events where the time scale of the event is relatively small and it does not accelerate appreciably. Okay, and in the case of when the Froude's number is less than 2, then we will use kinematic wave equation, and here the Froude's number is given as V by root G y. Okay. And in the case of dynamic waves, when inertial and pressure forces are important, then we use dynamic wave equation. This is used for generally movement of large flood waves and for longer duration. In the case of low acceleration and big deceleration become more significant. And it can be used with steep slopes or complex geometry where flow acceleration and deceleration are significant. Dynamic models provide more accurate representation of flow dynamics compared to kinematic wave models, as I have discussed before. So now let's look into kinematic wave celerity. So what is this? So first we will break this down. What is wave first? Wave is the variation in flow, that is change in flow rate or water surface elevation. It is called as a wave. What is wave celerity? Velocity with which this wave travels along the channels is called as wave celerity. Along the channel. So generally this value will range from 0.25 to 10 meter per second, and the dynamic kinematic wave model is model is, as we have discussed, dou q by dou x plus dou a by dou t is equal to q from continuity. And in case of kinematic equation, we are only considering the friction term. So the momentum equation will be S naught minus F SF. Okay. So here what we can do is, like in case of kinematic wave model, momentum equation is replaced by uniform flow equations. So for example, like Manning's equation. Then if in Manning's equation, we are putting S naught is equal to SF and R equal to A by P, then V equal to 1 by N into A power 2 by 3, P power 2 by 3 into S naught power 1 by 2. Remember the equation is, Manning's equation is V equal to 1 by N into R power 2 by 3, SF power 1 by 2. Manning's equations. Okay, so the Q will be equal to, multiply with area of the cross section, then you will get the discharge term. So it's 1 by N into S naught power 1 by 2 into P power 2 by 3 into A power 5 by 3. Simplies A equal to N into P power 2 by 3 by S naught power 1 by 2 whole power 3 by 5 into Q power 3 by 5. So this we can simplify and write as A is equal to alpha into Q power beta. And when you differentiate with, partial differentiate with respect to time, it will be alpha into beta Q power beta minus 1 into dou Q by dou T. Also from the continuity equation, we have written like dou Q by dou X plus dou A by dou T is equal to 2, right? So dou A by dou T is equal to Q. So this we put in this equation, then dou Q by dou X plus alpha beta into Q power beta minus 1 dou Q by dou T is equal to, this small q can also be written as Q by dou X, dq by dx. Okay, so here remember we are using partial differential, it's total differentiation that we are doing to get discharge in unit width, Q is. Okay, so from this, dx by dt is equal to 1 by alpha into beta Q power beta minus 1. Okay. Oh, sorry, I think I skipped a step. Let me just write it down. So this we can write as dou Q by dou X plus alpha beta into Q power beta minus 1 dou Q by dou T second. So this is equal to Q. And dq can be written as dou Q by dou T into dt plus dou Q by dou X into dx. Okay, so since we know from these two equations, dou Q by dou X plus dt by dx into dou Q by dou T will be equal to dq by dx, which is equal to Q. So from this, we can write dx by dt equal to 1 by alpha beta into Q power beta minus 1 and dq by dA is equal to 1 by alpha beta into Q power beta minus 1. So therefore, dx by dt equal to dq by dA. Okay. And also, kinematic wave celerity is defined as 1 by b into dq by dy from this. Then dA is equal to b into dy. So when observer moves at a wave's velocity equal to ck, then the small q, that is the discharge per unit will be equal to 0, and also dq by dx will be equal to discharge per unit width, that is small q. And in many cases, channel slope dominates in momentum equation. Therefore, flood wave moves as a kinematic wave. And in the case of dynamic wave celerity, so the speed at which a disturbance travels to the river channel is called as dynamic wave celerity, and it is generally dynamic wave celerity. It is a function of hydraulic properties of channels such as like slope, geometry, and flow resistant. Also, for gradually varying flow condition, dynamic wave celerity is also a function of local slope, which is varying along the channel. And in case of for rectangular channel, CD is equal to root GY. Okay, so if you see how the wave proceeds is that, so generally the main body of the flood wave is kinematic in nature, but there, if you see on the upstream side, the propagation will be the dynamic wave velocity will be in this side, but the flow of the water is V on the downstream side. So the flow of the wave will be V minus CD uh, at the upstream location of the wave. Okay. So the downstream propagation will be the flood wave will be moving downstream with the velocity CD, dynamic wave celerity velocity CD, and also the flow will be in the direction of downstream side, right? So this is also V and that is also V. So the downstream propagation velocity will be V plus CD. Okay. So the main body is kinematic in nature, but the dynamic wave moving downstreams are rapidly attenuating. And also here also if you see the dynamic wave moving upstream also is rapidly attenuating. So mainly the motion of flood wave has some key factors which are one, channel geometry, second, inflow hydrograph, channel roughness, and for the downstream boundary conditions. So now let's look into some modified Muskingum routing method, that is Muskingum Kunch routing method. It's given by Kunch in 1969, and here diffusion wave approximation is taken. Okay, their kinematic wave approximation is considered. Here we are doing uh, sorry, approximation. So O2 is equal to C naught O2 plus C naught I2 plus C1 I1 plus C2 O1. But here what we have is we will have a computational grid. Okay. So for time step J to J plus 1 and I to I plus 1 is the space scale. This side is space scale. This time scale. So here we have Qij that is at location I and time step j, we have the flow. And this is for the same location I, but at time step j plus 1, this is the flow value. This gives the flow at time step I plus 1 for, sorry, at location I plus 1 for time step j. And this is the flow at space at the next location I plus 1 and also at time step j plus 1. So here what we are doing is we are doing both time and space computation. Qi plus 1 j plus 1 is equal to C naught into Qi j plus 1 plus C1 into Qij plus C2 into Qi plus 1 j. So here C0, C1, C2 terms are like similar to the previous description, and K is equal to delta X by Ck, that is equal to delta X by dq by dA, okay, which is the approximate solution of the modified diffusion equation. And the X is, by solving it, we'll get approximate solution as 1 by 2 minus 1 by 2 times 1 minus Q by B into Ck is wave celerity, B is the width of the channel, S naught is the bed slope into delta X. Delta X is the like the space step. Suppose this is the channel, this is X1, location X2, X3. So this is the delta X term here. So these are used to solve the kinematic and diffusion wave equations. Okay. So is this clear, or if you have any questions related to flood routing, you can ask. Okay. So if there are no questions, let me proceed. So here, previously I have talked about this question. Here we are talking about, remember, it's hydrologic channel routing. They're asking. I got confused, like they were talking about hydrologic reservoir routing. So let me correct myself. So in hydrologic channel routing, they are asking what storage is a function of which of the following terms. Option E, outflow only. Option B, inflow only. Both outflow and inflow. Option D is outflow, inflow, and length of the reach. So the answer is it's a function of both outflow and inflow. So what is the storage volume of the channel section whose surface is parallel to the channel bottom called? So if you remember, this is the section. Okay, if this is the bed, then we are drawing a line parallel to it, and the storage that is falling in between these two parallel lines is called as prism storage, and the storage between the water surface level and this top part of the prism storage, okay, this is called as wedge storage. So the answer for this question will be prism storage, option A. So next question is, which of the following is true for the storage in channel section? Option A, both prism and wedge storage remain constant. Option B, prism storage changes and wedge storage is constant. Option C, prism storage is constant and wedge storage is changing. Option D is both prism and wedge storage change. So if you remember, we have have shown now also the prism storage will be constant because it's the volume between two parallel lines throughout the sections. Okay, but wet storage is the volume between the water surface and this top line of the prism storage. So which will vary at every location. So this wet storage changes, prism storage remains constant. Then the question is, next question is, if P is the prism storage, W is the wet storage, I is the inflow storage discharge, and Q is the outflow discharge, which of the following is true? If you remember, we have talked that prism storage is in case of prism storage, it is a function of outflow, but wedge storage is a function of inflow. So the answer will be option B. So which of the following units represents the storage time constant in Muskingum constant? That equation. So that is the term K. So if you remember, it should have same dimension as time. So here among these three options, second inverse, and meter cube per second, the one is time. The second is has the dimension of time. So option A. So next question is, for what value of weightage factor in Muskingum equation does the storage depends on outflow only? So here, if you remember, the equation is S equal to K into Xi plus 1 minus X into O, right? So they are asking what value of weightage factor, that is X. S will be only a function of outflow. So if x is equal to 0, then this term won't be there. Then it will be only a function of k into 1 minus x times of O. Since O x is 0, it is k into O. So therefore, the value of x's weightage factor is 0. So the next question is, in the find the storage time constant of the channel from the graph below. Here the weightage factor x is equal to 0.3, they said, and they're giving us the graph between storage versus xi plus 1 minus x into q. So s equal to k into xi plus 1 minus x into q is our equation from Muskingum method, right? So this is in the form of y equal to m into x. But here they have this, but here the x is this is written in y, and this is written in x system. So the slope will be whatever slope that you are calculating from this equation, you have to inverse it to get the k value. So k will be equal to 1 by m. Okay, so how you are calculating the slope value? So let's take these two terms. For this, the value is approximately, I'm assuming, 225, and for this the value is 500. So the slope is y2 minus y1 by x2 minus x1, that is equal to 60 minus 30 by 500 minus 225, is equal to 30 by 275, 0.1091 per hour. Okay, so as I've told, k is equal to 1 by m. So k equal to 1 by 0.1091. That is, once you calculate it, it will approximately come as 9.2 hours. So it's option B. Okay. The next is, they have said that the two Muskingum routing equations are 0.035 and 0.375. What is the third value? So if you remember, the sum of all the three quotients should be equal to 1. So 0.035 plus 0.375 plus the third quotient, let me assume as for C, then it should be equal to 1. So C is equal to 1 minus, so this term will be 0.41, that is equal to 0.59. So option B. Now they are giving us the inflow hydrograph of the channel. So here at each time step, what is the inflow values? And they have given the peak discharge from the reach of the hydrograph. We have to calculate using C naught equal to 0.03, C1 equal to 0.22, and C2 equal to 0.75. And they are saying the initial inflow and outflow at time t equal to 0 is 16 meter cube per second. So we know the equation is O2 equal to C naught O2 plus C1 O I1 plus C2 O1. Okay. So the inflow at time step 1 is equal to C naught I1 plus C1 I naught plus C2 O naught. Is So this is the equation. Here, this is the inflow at time step t equal to 1. This is at t equal to 0 and this is also at t equal to 0. So it will be 0.03 into 23 plus 0.22 into, they're saying initially the flow is 16. Inflow is 16 and plus 0.75 into outflow is also 16 initially. So the answer is 16.21 meter cube per second. Similarly, for outflow at time step 2, it's 0. C naught into I2. That is at time step 2. 30 plus 0.22 into at time step 1, that is 23. Inflow at 10. C is 2 into over. That is outflow at a time step 1. So which we have got here. 16.21. So it is 18.12 meter cube per second. So like this, we have to calculate outflow at time step 3 also. That is equal to 37 here. At previous time step, that is 30 plus 0.7 previous time step outflow, which we have calculated here, 18.12. Once you solve it, it is equal to 21.3 meter cube per second. So the outflow at time step 4 to calculate. So it's that it will be equal to 25.045 meter cube per second. Outflow at time step 5 is equal to 75 into 25.045 equal to 26.35 meter cube per second. Similarly, outflow at sixth time step is equal to, once you calculate, 25.83. So the answer will be 26.35. That's the peak flow. So here, next question is, they are saying that it's a rectangular channel with width 60 meters and S naught is given as 0.001, 1%, and Manning's quotient is 0.035. And Q is equal to 140 meter cube per second, which is equal to V into A. So for wide channels, we know R equal to Y and A equal to BY. So once you substitute in the Manning's equation, the equation will be something like this. So if you put the values in, so it's 1.16 into y power 5 by 3 into s power 1 by 2. So the y is equal to 0.88. The water depth is 0.88 meters. So and Q equal to VA. This implies 140 equal to V into area is B into Y. Right, so 0.88, so V is equal to 2.65 meters per second. Then we have to calculate the wave celerity, that is 1 by V into dq by dy, 1 by V into, so the equation will be S naught power 1 by 2 by n into 5 by 3 into y power 2 by 3. Once you calculate this, you'll get value as 4.37 meter per second. So also CD is equal to root GY, that is equal to root 9.81 into 0.88, 2.94 meter per second. So we have calculated CK, CD and also water velocity. Now we have to calculate the propagation, that is V plus or minus CD. So we know V and CD. What will V plus CD equal to? 2.65 plus 2.94, 5.59 meter per second. V minus CD is equal to minus 0.29 meter per second. Once you calculate this. Okay. So here they are saying Q equal to S by 4000. That's the relation between the outflow and the storage for a reservoir routing. And initially the inflow, outflow and storage terms are 0. So I1 is given as 300 meter cube per second at T equal to 3 hours. So from the continuity equation, it is I1 plus I2 by 2 into delta T minus O1 plus O2 by 2 into delta T is equal to S2 minus S1. So once you substitute the values, it is I2 is 300. Initially the inflow is 0 by 2 into 3 hours. So since it's in hours, you have to convert it into seconds. This is O2 by 2. Initially the outflow is 0. So 3 as S. So we know O2 is equal to S2 by 4000. So once you solve this, the equation will come around like this. Okay. This is S2, S2. So by solving this, the storage will be 6,87,361 meter cube. And since Q equal to S by 4000, the answer is the outflow will be 172.34 meter cube per second. Okay. So next question, I have solved the problem. Also, sir has discussed this problem. If you have any doubts related to this problem, you can ask me. Uh, so basically here what we are trying to do is they have given the elevation storage and outflow terms. So for Reservoir routing, we know we have to first calculate S plus O into delta T by 2. So first we are using the storage and outflow terms, and I'm assuming the delta T is equal to 6 hours in this case. The S plus O into delta T by 2 values are calculated, and make sure that delta T should be in seconds also. So 6 into 3600 we have to do because the input data is in meter cube per second. Okay. Then after that we have plotted the storage versus outflow curve and also outflow versus S plus O into delta T by 2. And by plotting it using the trend line in the Excel, I have gotten the equation of the slopes also, of the line also. Then what I was doing is, since they have told that inflow is having at I equal to 0 and t equal to 0, at t equal to 0, I equal to 0, and at t equal to 18 hours, there is a peak discharge of 24 qmax, and at t equal to 36 hours, the inflow is then. So what I was doing is I have issued, since it's a triangular inflow hydrograph, t equal to 0, t equal to 18 hours, and t equal to 36 hours, we know 6 to 12, the slope of this line will be 4 by 3. Okay. So using that you can calculate the values of the inflow hydrograph. So like this, I got the inflow hydrograph values and I1 plus I2 by 2. So these two values, by averaging them, I got I bar, then multiplying with delta T, then I got this value. And then also initially I'm assuming the outflow is 0. Okay. From that, corresponding to the 0, what is the storage term? So if the x is equal to 0, y is equal to 45,000. So like that, I'll calculate the storage term also. And once you have storage term and outflow term, S minus O into delta T by 2 can be calculated. And once you get this one, so the equation is I1 plus I2 by 2 into delta T plus S minus O into delta T by 2 is equal to S plus O into delta T by 2. So we can calculate this also by adding the columns 4 and 7. We'll get this. So from this equation, you know what is the X term. So corresponding to Y term can be estimated. That is the outflow value. So whatever outflow that you are estimating will be written in this time step. So like this, again we will average the inflow, get I bar, and corresponding to O, we know the storage term from the previous graph and calculate this, and then we will calculate this by adding the columns 4 and 7, and by using the previous graph, we can get the outflow term corresponding to this value. So like this we will calculate, and now we are drawing the hydrograph of inflow and outflow. You can see both the peaks are occurring at the same time step, but there is a peak attenuation which is equal to 24 minus 22.73, that is equal to 1.27 cubic, and there is no time lag. So that's how you need to solve this problem. If you have any doubts, you can ask me, or let's end this session. Let me wait for 1 or 2 minutes. If you have any doubts, you can raise the hand or you can message in the chat box also. So if there are no doubts, let's end this session. Thank you for attending.